I continue introduce the programmable controller. This is a programmable logical controller. And last time I introduced the programmable logical controller. Sometimes we call the programmable logical controller programmable controller. The abbreviation is PC. But the PC is the same as to the personal computer. Personal computer. So we call the PLC. PLC. Programmable logical controller. Logical controller. Here is some picture about the PLC. PLC. Programmable logical controller, also called programmable controllers or PLC, are solid-state members of the computer family. Using integrated circuit instead of actual mechanical devices to implement control function. Control function. They are capable of storing instructions such as sequencing, timing, counting, arithmetic, data manipulation, and communication to control industrial machines and processes. Storing instruction. Instruction include sequencing, timing, counting, arithmetic, data manipulation, and communication. Communication to control industrial machines and processes. PLCs are industrial computers. Essentially, the PLC computers is computer with a special designed architecture in both their central unit and their interface circuit to field devices. Central unit. Central unit is the some devices consist of computer, and the interface circuit to the outside devices. This is programmable logical controller or programmable controller. Input a signal from the process or machine, or just from the manipulation. Output to the process or machines. Here is the example. Use the PLC to control lights, motor, and pump. The PLC accepts the signal from the sensors or from the button. The PLC fundamentally is a computer, or which consists of a microcontroller, microprocessor. This is a historical background. General motto specified the design criteria for the first programmable controller in 1968. 1968. Their primary goal was to eliminate the high costs associated with inflexible relay controlled systems. Initial specification included the following. The new control systems had to be price competitive with relay systems. The systems had to be capable of sustaining an industrial environment. The input and output interface had to be easily replaceable. The control systems needed to be pass stage connection to a central systems. The system had to be reusable. The method used to program the controller had to be simple, which means the program for the PLC is simple. The first PLCs offered relay functionality, thus replacing the original hardware relay logic, which used electrically operated devices to mechanically switch in electrical circuits. The methods requirements of modularity. Modularity means we can replace part of the PLC. Expandability. Add the more module to the PLC. Programmability. Program for the PLC. Ease of use in an industrial environment. Easy to use. Easy of installation. Use the less space. The device is compatible. Compact. Or reusable. We can change the program and change the purpose. The controller programming about the neutral tedious had a recognizable plant standard. The ladder diagram format. The ladder diagram format is like the electrical diagram. By 1971, PLCs were being used to provide relay replacement as the first steps towards control automation in their industries, such as food and beverage and metals, manufacturing and pulp and paper. Many technological advances in the programmable controller industry continue today. Change include both hardware and software. Two parts, hardware and software. fast the now the PLC faster scan times faster scan times small no cost PLCs with more power high density input output systems intelligent microprocessor-based I/O interface, such as PID, network, and host computers. Mechanical design improvements have included rugged input-output enclosures and input-output systems that have made the internal and integral units made the terminal and integral units as introduced easy of program for the PLC. I give you some example in the microcontroller. If we want to make a program about the PID or network as we know, it is difficult for us to write the codes, but in the PLC, we just just pick up the module, in the from the supply, and make the PID control or networks. That's easy for us to write some code, complex code. Special interfaces have allowed certain devices to be connected directly to the controller, such as thermocouples and string gauges. Peripheral equipment has improved operator interface technique. Historical background. This is some programmable controller family. Software enhancements. Object-oriented programming tools have been incorporated. Powerful instructions have been provided. High-level languages such as Basic and C have been implemented. Advanced functional block instructions have been implemented for ladder diagram instruction. Object-oriented programming. We can just pick the object-oriented code and make our own program. Powerful instruction. High-level language have been implemented. In the when we make a PLC program, we can use some high-level language, or just use some language like the high-level language. Advanced functional block instruction have been invented for ladder diagram instruction. diagnostic and fault detection have been expanded, has been expanded. Diagnostic fault detection, floating point math has made it possible to perform complex calculation. In the microcontroller, we made a floating plot math is difficult, but in the PLC, we can just pick the math, module and make the program. Data handling and manipulation instruction have been improved and simplified. PLCs are being incorporated into computer integrated manufacturing systems. Robots and CAM systems advanced in PLC technology include features such as better operator interfaces, graphic user interfaces, and more human-oriented machine interfaces such as voice modules. Advanced includes development of interfaces that allow communication with the equipment, hardware and software that supports artificial intelligence, such as fuzzy logical, some artificial intelligence. Some artificial intelligence is integrated to the PLC, integrated to the PLC. New PLC instructions are developed out of the need and add intelligence to a controller. The future will almost certainly continue to cost programmable controller as an important player in the factories. Important player is the factory. Next, I introduce the principles of operation. The PLC include the central processing units and input and output when the PLC are running, the central processor units execute the program time by time from the start. When the central units execute the program started from the beginning. And first check the input status, check the input phase, and after the CPU check the input states, and add the input states to the program and calculation. After the calculation is finished, give the result to the outputs. After the result is given to the outputs, the CPU start the program again. Start the program again. Is the principles of operation. PLC. PLC. This is a block diagram of major CPU components. CPU includes the power supply, processor and the memory. Processor and the memory. The fundamental components are fundamental components. Just like the computer. The computer we need the CPU, microprocessor, memory, and then the power supply. Power supply. The input-output systems form the interface by which field devices are connected to the controllers. The main purpose of the interface is to condition the various signals received from or sent to external field devices. The purpose of the interface to condition the various signal received from or sent to external field devices. In incoming signals from sensors, push buttons, limit switches, analog sensors, signature switches, and some wheel switches. Are wired to the terminals on the input interface. The device that will be controlled, like motor starters and solenoid waves, pi notch lights, and position wires are to the terminals of the output interface. The system power supply provides all the voltage required for the proper operation of various central processing unit sections. This is a PLC input-output interface. Input module accepts the signal from the external field. The output module sends the signal to the external field. And this is the microprocessor and the power supply. Scan cycle. When the PLC work, the scan cycle start from the beginning of the program, read the inputs, execute the program, write the result to the output, start again. This is the scan cycle for the PLC. PLCs versus other controllers. Is there a need for flexible in control logical change? is there a need for high reliability? Space requirements are important. Increased capability and output requires zero data collection requirements. Will there be frequent control logical change? Will there be a need for rapid modifications? Must the similar control logical be used on different machines? Is there a need for future growth? Is there a need for future growth? What are the overall cost? This is some question about the use of controller. This some of the characteristics for the PLC. For example, the PLC is flexible in control logical change. High reliability. And compact, and increase the capability and the outputs required can send the signal outputs increase the capability when the program is changed, the ability is changed. Data connection. The PLC can connect data and send the data to other devices. We can change the logical states frequently. Rapid modification. If we want to change the logical, the system logical, we can change the program. We can change the program. Similar control logical on different machines. Future growth. And the costs is no. However, when we buy also we buy PLC, the PLC is expensive, but the PLC is reliability. We can use it for almost 10 years, 20 years. So the overall cost is no. The PLC applications are automotive, chemical and petrochemical, glass processing, manufacturing and material handling, maintenance, power, pump and paper, rubber and plastic. We can see the PLC can use in many industrial processes. The PLC application are automotive, internal combustion engine monitoring, carburetor production testing, monitoring automotive production machines. Power steering, valve assembly and testing. assembly and testing. The PLC can use it as a controller in the automotive. PLC application chemical and petrochemical dyes chemical batching fan control gas transmission and distribution pipeline pump station control oil field. Applications are in manufacturing and machining. Production machines transfer line machines, wire machines, tool change, plant spraying. PLCs applications in power. Plant power systems, energy management, core fluidization processing, compressor efficient control, in a word, the PLC can use in many industrial environments. Next, I introduce the ladder diagram and the PLC. Ladder, the programming language for the PLC. Ladder diagram. The ladder diagram represents electrical sequences of operation. These diagrams represent diagrams represent the interconnection of field devices in such a way that the activation or turning on of one device will turn on another device according to a predetermined sequence of events. This is a simple electrical ladder diagram. From this diagram, we can see if we push this button, and this switch is on. The ladder is on. If this switch is off, this switch is on, and this button is not pressed. This light is on. The current is flow along this line. The PLC, the diagram, ladder diagram is almost the same as to this electrical diagram, ladder diagram. Ladder diagram and the PLC, the diagram and the PLC. This represents the input module. S represents the output module. If this is the inside of the PLC, this is the inside of the PLC. The external signal input the PLC input the PLC, and the PLC execute the program and output the result to the external field. External field. This is a actual PLC. Electrical connection. Electrical connection diagram. This is the input module. This is the output module. Output module. This is the switches. Button. Switches on the button. And this is outputs coils. This net output coils. Net and we can use it. Use the controller to control the output. And this PLC exit the external signal. This is some Nando diagram. In the comparison, the electrical diagram, electro Nando diagram, and the PLC Nando diagram. This is switches. This is switches. This is soil. We can compare. This is a serial connection. Serial connection. Here is a parallel connection. This is a parallel, and the output to the connected to the output. This is at one else in series. Here is parallel. Here is serial. Here is the serial. So we can transfer this. From this comparison, we know the electrical diagram and Nando diagram is similar to the PLC Nando diagram. So if we want to make some Nando diagram, we can just imagine the switches and the soils. Okay, everyone.
Yes, 老师。
Yes, 老师。
Let's have a break.
OK， 老师。
谢谢老师。OK， 老师。
Okay, let's have a break. Hello.
Yeah, 老师。
Let's continue.
Sure, sure.
Last class, I introduced the diagram in this is the net diagram I introduced in last class. Now I give you a simulation. You can easily understand the diagram, net diagram. I change the program to English. This is a net diagram. I simulate this diagram. Click here. Is that the normally open? Normally open. Here is this is a simple net diagram. And I haven't introduced the address. Address before we simulate this program. I give you some conception about the address. In the Siemens PLC. The input address is start with the I input I. The output address starts with Q with Q. So this is normally open. This is normally open. I give you the normally open I 0.0. This normally open 0.1. This is the output. Output. I give the address Q 0.0. 0.0. So if I want to simulate this program, I export the export. This is a program. Introduce the access code. This code 6596. 6596. So CPU type, we can give some kind of CPU type. Node program. This is some error. Files cannot open to read digits. As I see before, this program not come from the Siemens. Not come from Siemens. So there is some error when we use it. This error cannot affect the simulation. So we don't care it. This is a program. If we want to simulate the program, we can start here, run. Run. There is it's I 0.0. This is I 0.1. I give you the 0. 0. You can see 0. 1. 1. I give the stage 1. You can see if the I 0.0, I 0.1 accept the signal from the outside. The Q is gets the signal. So you can see you can see the energy flow. Energy flow is flow from the left side to the right. Left side to the right. If the well is connection, well is connected, the power energy is flow to the output, flow to the output. We can change. You can change the state. We can see if I open I 0.1 there is the well is not connected. Is not connected. This is how to simulate the S7 200 smart PLC. If we want to simulate, for example, if we want to simulate this one, we can simulate again. if what I want to select. Sorry, I want to place this program on the top. I use another. Sorry, I cannot put the PPT on the top. I just change the program. This is normally open. This output. We just connected. This normally open to here. Just put the normally open to here. Sorry. Yeah, normally open. I 0.2 sorry. Now you can see this is program like this one. Save the program and export the POU EX2 Loaded program. Let's delete program. Load program. Load program. It's 012 012 if switch on I 0.0 I 0.0 sorry put the run the PLC run the PLC 0, 1 0, 1 you can see if the I 0.0 is switched on, I 0.1 is switched on, so the output Q 0.0 gets the signal. If I 0.2 I 0.2 is signal and I 0.0 is switched off, also gets the signal from the left to the right, left to the right. If we switch the off 0, 1, yeah, the output is no signal. There is no signal is output. This is a simple simulation about the net diagram. Net diagram. Oh, sorry. Next, introduce the PLC advantages. PLC advantages. The PLC advantage inherent features. Inherent features solid state components. Solid state component, which means high reliability. High reliability. The solid states made it high reliable. High reliable. Programmable memory. Programmable memory simplifies the change. Flexible control. Make the program control the process or some industrial environments. We can change the program and change the control. Change the program. Small size. Minimal space requirements. Minimal space requirements. Microprocessor based. That's processor based. Communication capability. Higher level performance. Higher quality products. Higher quality products. Multifunctional capability. Multifunctional capability. Software timers and the counter estimate eliminates hardware. Eliminate hardware. Easily change preset. Easily change preset. Software control relay. Software control relay. Reduce hardware wearing cost. Software relay no need the where monitors where and reduce the space requirements reduce space requirements modular architecture modular architecture made it easy to install easily installed reduce the hardware cost expandability variety of I/O interface control a variety of device eliminates customized control eliminates customized control remote I/O station eliminates non-well conducted run diagnostic indicator reduce the troubleshooting time signal proper operation modular I/O interface neat appearance of control panel easily maintained easily wired quick I/O disconnection disconnect servers without disturbing wiring system variable stored in memory data useful management or maintenance can be output in report form just output the data is a report form this is a PLC advanced easy of installation just hang on the frame this is easy to install remote I/O connect the different PLC with the communication well so remote I/O use the PC as a program device after the to make the program then after the program is made download the program to the PLC download the program to the PLC okay this is some introduce about the introduction about the programmable controllers next I introduce some fundamental knowledge when we use it the PLC when we use it number systems as we know we in the knife we use it the decimal but in the computer we use the binary the number systems programmable controller use binary numbers in one form or another to represent various codes and qualities. Every number systems has a base. We use the binary. The base of the number system determines the total numbers of Unicode symbols used by that systems. This is the decimal number systems. Which value is equal to base and the power of position, power position. This position is 0, 1, 2, 3. So this value is power of 10 power of 0. 10 power of 0. 0. This is the decimal number systems. Decimal number systems. Decimal number systems. We use it. We can represent the decimal number systems like the value in the bits and multiply 10 power of 10 power. As decimal. So similarly, we can represent the binary number systems. The binary number systems use the number 2 as the base. 2 as the base. That's the only number digital as 0 and 1. 0 and 1. In the binary number systems, 8 bits. 8 bits we call the bytes. 8 bits we call the bytes. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits we call the bytes. We call the bytes. Call them bytes. This is 1 byte. 2 bytes. So 2 bytes. 2 bytes we call it a word. Call it a word. A word. This is important in the PLC. We understand the binary systems. Binary systems. As I simulated the program, I give the address I 0.0, which means the first I means inputs the first the 0 is byte 0 byte 0. So the point 0 is the bytes the first digit 0 first byte 0. So the 1 byte has 8 bit 8 bit. So point 0, point 1, 2, 3, 4, 5, 6, 7, 7, which means the input address is start in I point 0 to I point 7 I point 7 I point 7. It is left is the most significant bit. It is right end is the less significant. Here is the most significant. Left end is the most significant bit. The right end is the least significant bit. Least significant bit. Just similar to the decimal number systems, we can represent the below like this. Like this. Next, introduce the octal number systems. Octal number systems use the number 8. Use the number 8 as its base. With its 8-digit being 0, 1, 2, 6, 7, 8, 5, 6, and 7. We can represent the octal number system similar to the decimal. Hexadecimal number systems hexadecimal number systems use 6 as its base as its base. As we know, the 4 bits we can represent the 4 bits with one hexadecimal one hexadecimal bit. So you can easily to convert the binary to the hexadecimal. The hexadecimal number systems hexadecimal from 0 to F. In the decimal, we use the number 0 to 50. 0 to 50. Number conversions. To convert a decimal number to its equivalent in any basis, you must perform a series division by the designed base. Perform a series of divisions by the designed base. The conversion process starts by dividing the decimal number by the base. If there is a remainder, it is placed in the least significant digital rightmost right end position of the new base number. If there is no remainder, a 0 is placed in the least significant digital position. The result of the division, is then brought down, and the process is repeated until the final result of the successive division is 0. This is an example. Sorry, I need to answer this phone. This is an example numerical conversion example numerical conversion example convert this decimal to binary conversion decimal to binary the binary equivalent of the decimal number is 65 we can convert the 65 to the binary 1 0 0 0 or 1 1 we can divide the 65 by 2 65 by 2 divide 65 divided by 2 we can get the result 70 remainder is 1 remainder is 1 so repeat the precise 17 divided by 2 we can get the result 8 remainder is 1 remainder is 1 so repeat the process we can get the remainder 11000 we can read write the as the binary 100 11 this is an example convert decimal to the hexadecimal divided by 16 divided by 16 here is the remainder we can write the 355 to 54b 54b negative numbers consider decimal number consider decimal number 23 or binary what about the minus 23 minus 23 if a minus sign is placed in front of the number as we do with decimal number this method is suitable for us but is impossible for programmable controllers and computers to interpret since the only symbols they use are binary 1 and 0 1 and 0 therefore 2 complement is used the 2's complement use an extra digit to represent the sum in the 2's complement computation each bit from right to left is inverted only after the first one is detected from right to left is inverted only after the first one is detected let's use the number plus 22 decimal as an example this plus 22 we can change it to the binary like this if the 2's complement would be uses this is sum this is a sum bit this is sum bit here is the binary if we use as the complement we can change back each bits is inverted this is 0 inverted an important requirement of programmable controller is communication with the various extra I/O devices. This input-output function involves the transmission, manipulation, and storage of Billiard data that at some point must be interpreted by humans. Biliary coding is the process of assigning a Unicode combination of ones and zeros to each number, net, or symbol that must be represented. The most common code used in the industrial is ASCII, BCD, and GRI, ASCII, ASC2, alpha numerical codes are used when information processing equipment such as printers and cathode ray tube, CRT, must process the alphabet along with the numbers and the special symbols. These alphanumerical characters are 26 letters uppercase 10 numerals 0 to 9 plus mathematical and punctuation symbols can be represented using 6-bit code. 6-bit code. 6-bit code the 2 power of 6 is equal to 64 possible characteristics. The most common code for alphanumerical representation is ASCII2. The American Standard Code for Information Interchange. Although an 6-bit code can accommodate the basic alphabet numbers and the special symbols. Standard ASCII characters set use 7-bit code. 7-bit code. 2 power of 7 is equal to 128 possible characteristics. Characters, which provides room for lower case and control characters in addition to the characters already mentioned. BCD code. Biliary coded decimal. BCD systems was introduced as a convenient way of human to handle numbers that must be input to digital machines, interpret numbers that are output from machines. This is decimal. This is biliary. from here we can see use 4 bits. 4 bits represents the one BCD code. One BCD code. Similarly, like the hexagonal hexadecimal. Hexadecimal. Yes, the 7 segment indicate the field device and some will switch. Some will switch. We can use it as the binary. And this one decimal can change, convert to 4 bits. 4 bits. Okay, everyone.
Laoshi, we're here. I'm here.
Have a rest.
Yes, Laoshi. Yes, Laoshi.
Oh, okay. For how many minutes, also?
20 minutes.
All right. Okay.
Hello. Hello, everyone.
Hello, 老师。
Let's continue our class.
OK。
The Greek code. Greek code. Greek code is basically a modified binary code where only one bit change as the counting number increasing. This reduces the change of error. Therefore, it is a suitable primary for precision transducers. Precision transducers. When we use the sensor coder, this is the Greek code. Greek code. This is the Greek code. 0 is 0 1 is 1 Greek code 1 is 1 0 1 1 is 1 0 1 0 is 1 1 is 1 1 this 1 1 0 is 1 0 0 so this is Greek code is different from the binary is different from the binary. Next, introduce register word formats. Register word formats as I see, the one word has 2 bytes. 2 bytes. So one word has 16 bits. Has 16 bits. Programmable controller perform all internal operations in binary formats using ones and zeros. In addition, the status of I/O failed devices is also read and written. In binary form to and from the PLC's computer. Generally, these operations are performed using a group of 16 bits. Group of 16 bits. A PLC was also called a register. Register word formats. A PLC word 16 bits. Called a register. The first bits, the least significant bits is 0. 0 bits, 1 bit to the 15 bit, 15 bits. The first 8 bytes called least significant bytes. The second byte called most significant byte, most significant bytes. This is introduced for the binary systems. In this chapter, we need to know the relation between the decimal system, binary systems, octal number systems, hex decimal number systems. Next, introduce logical concepts. Logical concepts. Logical concepts. Binary concept. Binary concepts. In digital systems, two state conditions can be thought of as a signal that are represent or not represent, that are represent or not represent, or activated on, not activated off. These two state concepts can be the basis for making decisions. And since it is very adaptable to binary number systems, it is a fundamental building block for programmable controllers and digital computers. Binary 1 represents the presence of a signal. Binary 1 represents the presence of a signal. Or the occurrence of some events, where binary 0 represents the absence of the signal, or non-occurrence of the event. In digital systems, these two states are actually represented by two distinct voltage levels. Two distinct voltage level minus 5V and 0V minus V positive logical and negative logical plus V represent operating, the 0 represent not operating, the 1 represents ring, 0 represents not ring, 1 represents on, 0 represents off, 1 represents blowing, 0 represents silent, 1 represents running, 0 represents stop, 1 represents engaged, 0 represents disengaged, 1 represents closed, 0 represents open, 0 represents open. The two states, which means we can represent two states with 1 and 0, 1 and 0. Logical function, operation performed formed by digital equipment such as programmable controllers are based on three fundamental logical functions and or and not and operation zero and zero which gets zero and one gets zero 1 and 0 gets 0 1 and 1 gets 1 which means and operation every bit is 1 we can get 1 or we can get 0 and gates only true 1 gets the result 1 gets the result 1 in the electrical circuit we can represent the relation like this we also can represent the relation in the PLC ladder diagram PLC net diagram all gates we can see 0 or 0 gets 0 or 0 1 gets 1 1 0 gets 1 and 1 1 gets 1 from here we know only if there is 1 exists we can get the result 1 get the result 1 the electrical ladder circuit not just get the inverse here are some example for the logical function example show the logical gates true table logical gates true table here's true table not true table and true table true table represents the all possible states and shows the logical gates true table and the circuits representation for solenoid valves that will be open if select switch S is on and if never switch L is not on never switch L logical function example from this relation we can get the results logical representation the S1 and the L1 is and relation relation V and relation V1 only the we can check the truth table check the truth table the S is 0 the L is 0 we can get 0 the S is 0 L is 1 we can get 0 S is 1 L is 0 L is 0 S is 1 S is 0 some maybe there's some error we can get this 0 this is 0 this is 1 1 we can get the 1 this is some example for how to show the relationship between the S and S1 and L1 S1 and L1 this is some example for the alarm horn if the alarm horn is the two button is and relation to and relation we can draw the electrical NAND like this next introduce the N and N or gates N and N and N or gates just add the nut just add the nut it is a result of and or and or and in the AND operation, we can get this is 0, 0, 0, 1. So not the operation 0, 0, 1, 1, 0, 1, 1, 0. N or truth table when we are A or B A or B, we can get the 0, 1, 1, 1. Add the or not add not operation add not operation we can get 1, 0, 0, 0, 1, 0, 0. Some principle of Boolean algebra and logical Boolean and algebra sometimes we can use the Boolean algebra represent the relation represent relation so sometimes we can change the logical state to the Boolean equation Boolean equation this is AND this AND operation we can AND operation use the Boolean equation A multiply B A multiply B This AND use multi-pair and OR use add not use bar on the natural the bar on the natural. This is another representation for the logical relation this combined gates we can combine the gates this and this is or and or A B and add C A B add C this N and A B add a bar on the top of AB on the top of AB This is this is all this is and this is all and all and n or and n or and combined gates combined gates some Boolean algebra rules some Boolean algebra rules commutative no we can change the position of two operator to operate two number change the two number position associate no we can add the two number before or can add the two number before this is association no it's the Morgan laws we can change the A add B and under the not to AB not AB not so this is some Boolean algebra rules the Boolean algebra rules use it to represent the logical relation sometimes if the logical relation is complex we can use the Boolean algebra rules to simplify the relation next introduce the PLC circuits hardware logical refers to logical control function hardware logical refers to the logical control function timing sequencing and control that are determined by the way devices are interconnected hardware logical is fixed and can be changed only by altering the way devices are physically connected PLC circuit this is a hardware related logical circuit hardware related circuits the logical control function determined by the way devices this the devices on the way determines the final state only the states can be changed. The state can be changed only by altering the way devices are. Altering the way devices are. When the devices on the way is changed, the logical can be changed. So this is a hardware circuit. Hardware logical circuit. This is, for example, if only this device and this device only after this device is connected, this one can be connected to this, the two devices connected. Only this one is connected here. The device after the this one is connected to this line, connected to this Y. Prime function of PLC, prime function of PLC is to replace existing hardware control logical and to implement programmable control function for new systems. The prime function replace existing hardware control logical. The hardware controlled logical in the PLC can be replaced by the PLC logical, PLC logical, software logical, software logical. How these instructions are implemented to convey commands to the PLC is called the language. Is called language. The most conventional of the control language is ladder diagram. The most conventional language ladder diagram. We can just convert the electrical hardware logical to the ladder logical to the ladder language, ladder diagram language. Ladder diagram are also called contact symbology, since their instructions are really equivalent contact symbols. The complete ladder circuit can be source of individual circuits, each circuit having one output. Each of these circuits is known as a run, or network, Therefore, a run is the contact symbology required to control an output in the PLC. Each circuit having one output. Some controllers are all know a run to have multiple output, but one output per run is the convention. I show you in when we made the program. This is the network network 1 network 2 network 3 according to the PPT we know one network only one output maybe some controller know wrong or a network have to have multiple outputs but one network has one output is the convention is the convention in the PLC code some input device and the output device we can use it is a button as input device signature switch limiter switch proximity switch timer contact we can use it as input devices output devices are pi notch night valve horn relay control relay and the timer timer is the output device timer contact input device input devices this some circuit show you the the logical this is a electrical circuit we can change the electrical circuit to the PLC NAND diagram PLC NAND diagram and connect the input to the left and put the output it is right you need understand the relation the electrical ladder and the PLC ladder diagram if you can understand the relation you know how to convert your electrical diagram to the PLC ladder diagram PLC ladder diagram PLC circuits and contact logical note that the PLC diagram includes all the field inputs and output devices connected to the interface that are used in the ROM. A complete PLC NAND diagram program consists of several runs also network each run controls an output interface that is connected to an output device each run is a combination of input conditions or input symbols connected from left to right between two vertical lines with the symbol that represents the output at the far right just like this this is left 9 this is left 9 sometimes we don't draw the right line. We don't draw the right line. Just put the output at the far right. At the far right output. At the far right. Next, I introduce the PLC addressing. PLC addressing. Each symbol on a run will have a reference number, which is the address in memory, where the current state for the reference input output is stored. Output is stored. When a field signal is connected to an input or an output interfaces, its address will be related to the terminal where the signal well is connected. Field signal connected to an input or an output interface, its address will be related to the terminal, related to the terminal where the signal well is connected. Consider a simple circuit. Consider a simple circuit. Each real field device, push button PB1 and PB2, limited switch LS1 and the panels nice PL1 is connected to the PLC's input and output modules, which have a reference number, the address. To turn PL1 on, one of the following conditions must occur. PB1 must be pressed and LS1 must be closed or on. PB2 must be pressed and LS1 must be closed. This is the condition for the PL1. In the PLC control program, power must flow through either address PB1 and PLS1 or through address PB2 and LS1 to turn on output. In the actually logical, this is actual logical. Output 40 output 40 energize the night PL1 that is connected to the interface with the address 40 In order to provide power to address 30, 31, or 32, the devices connected to the input interfaces address must be turned on. Next, introduce the contact symbols. Contact symbols. Okay, everyone.
Yes,
Yes,
老师。
老师。
Yes, 老师。
Today I introduce too much. Okay,
Yes,
let's finish our today's class.
Yes,
，OK，老师。
Okay.
Okay, 老师，no problem.
See you.
Actually,
next week.
This PPT, we have it.
Yes, Lord.
Okay, I will share this PPT in the WeChat. Okay, in the net meeting
Okay,
chat in the net meeting chat
Okay, 老师 thank you.
that's okay.
Carlos. I'll answer the following question. It's about C master and C question. The discussion of the origins of question.
Pwede abar simkan yung variable.
They have provided a lot of useful facts. They have been a major contribution. Sure that is not esteemed. Gee, scientists. mention a huge garbage patch in the Pacific.
Lava, be careful.
Give an example of man-made pollution in the oceans. Explain why few fish live in the Pacific Ocean. Illustrate the vast size of the Pacific Ocean. Indicate the difficulty of operating on trunks. Oh,
Lava.
you, but class finish. Why you until why you still here? Every time when I forget to mute my microphone, you already know.
And we're doing a lot of shit.
You don't know what I'm doing, that's why.
Bro, be
But
careful,
thanks,
huh?
okay? Let me mute.
Class is not over.
Come again?
Class is not
What
over,
you
bro.
say? The class is over, of course, like she say.
Really?
Yeah, or you went out here, maybe. The class finished.
Don't joke. I was waiting for him all the time. Hmm.
This shouldn't be too sensitive.